Hello everyone, I am Hongjia Jai from Zhejiang University. Today, I will introduce our work, NIS-SLAM, Neural Implicit Semantic RGB-D SLAM for 3D Consistent Scene Understanding. Previous implicit-based neural SLAM, like IMAP and NIS-SLAM, just only reconstruct the geometry and appearance information and do not model semantic information. Recently, some work pay attention to model semantic informations, like VMAP, NIDS, NIS-SLAM. But they use GT semantic, instance information to model it. However, GT information is often not available in real scenarios. Therefore, we wonder if we can recover the camera pose, scene and object level reconstruction, and consistent semantic field learning only from the RGB-D image sequence. An overview of our approach is shown in figure. Our system take RGB-D monocular data as input, and we use the pre-trained CNN semantic segmentation model to generate inconsistent noisy semantic results of multi-view images. Simultaneously, we can performance camera tracking and geometry and semantic reconstruction. Next, we will introduce our method from 3 parts. The first part is the hybrid implicit scene representation. We use high-frequency parametric encoding and low-frequency positional encoding to represent the scene. The second is the multi-view noisy semantic fusion strategy, which can lead to more consistent semantic observations. The last one is the loss function and optimization strategy. In order to better fit the geometric surface, we use a hybrid encoding of high-frequency tetrahedral encoding and low-frequency positional encoding as our scene representation method. The basic element of mesh is triangular primitive. Compared with cube, using tetrahedral encoding can better fit the surface. To model information at different scales, we concatenate multi-resolution features that obtained via barycentric interpolation. Our system consists of 3 decoders: geometry decoder, color decoder, and semantic decoder. The inputs of different decoders are shown in the figure. Next, we introduce the multi-view semantic fusion module. As shown in the black box in the figure below, the semantic segmentation network may produce inconsistent and noisy 2D prediction results for RGB images from different views. In order to learn a more consistent semantic field, we project the semantic prediction information of adjacent frames to the key frame, and obtain the fused multi-frame semantic observation information based on the corresponding confidence via softmax function. In this part, we show our loss functions. Reconstruction loss of color and depth, which perform pixel-by-pixel optimization between rendering results and ground truth images. The second is the SDF and free space loss, which can learn an accurate geometry filed by optimizing the signed distance function. To enforce spatial smooth of the parametric encoding, we apply the smooth constraints on features. Finally, we apply the semantic reconstruction loss to optimize the 3D semantic field based on single-frame and multi-frame semantic prediction. We apply 2 optimization strategies for our system. We use the segmentation confidence to guide pixel sampling, which can avoid areas with large errors during camera tracking. Besides, we use progressive optimization strategies to make loss convergence stable. The high-frequency information may lead to suboptimal results when the initial pose is far away from the ground truth. In the following, we show our experimental results from different aspects. We show the camera tracking result of ScanNet, Replica, and TUM RGB-D datasets. It can be seen that our method can achieve relatively stable and competitive results. On ScanNet dataset, our performance is only worse than Vox Fusion. On Replica dataset, only one scene achieves the second results, and rest scenes achieve best results. On TUM RGB-D dataset, 2 scenes achieve the best results. We show the tracking and reconstruction process from top views. The top and bottom parts show the scenes from ScanNet and Replica datasets. The red color shows the camera pose and trajectory estimated by our tracking process. The geometry and appearance of the scene are reconstructed by our mapping process. As shown in the figure, our method is able to reconstruct high-quality geometric surface and color texture information from monocular RGB-D sequences. We show the camera view rendering results of the reconstructed geometry. The 8 scenes are from the replica dataset. As shown in the figure, our method is able to reconstruct a 3D consistent geometric surface. We show the camera view and top view rendering results of the reconstructed geometry. The selected scenes are from the ScanNet dataset. As shown in the figure, our method is able to reconstruct a 3D consistent geometric surface for challenging real-life scenarios. We show a portion of the reconstructed object surface. We rendering the reconstructed object mesh from different views. These objects are extracted from our segmentation decoder. As can be seen from the figure, we are able to model a 3D consistent semantic field, which can aid us to extract 3D semantic objects. We show scene level and object level reconstruction results on replica dataset. As shown in the table, we achieve the best performance on completion and completion ratio for all scene for scene level reconstruction. Only accuracy metric is worse than point-SLAM. Due to point-SLAM use TSDF fusion as the post-process, which will lead to better accuracy. For object-level reconstruction, our approach achieved the best results on all metrics. We show some visualization results of scene-level and object-level reconstruction results. From the figure, we can know that our approach can generate more high-fidelity surface and fill the whole of unobserved regions due to the smooth prior of our neural representation. We show the semantic segmentation result on replica. From the figure, we can see that compared with the baseline, our method can better model a 3D consistent semantic information field. It can remove semantic noise information during reconstruction and inconsistency of different views. We show the results of neural rendering results of color, depth, and semantics. It can be seen from the video that we can reconstruct the geometry and appearance information of the scene very well. And at the same time, we can recover a 3D consistent semantic field from the noisy 2D semantic information. Compared with the baseline, our method can better model a 3D consistent semantic information field. It validates the effectiveness of our multi-view fusion approach. In this part, we show the augmented reality applications of our method. Augmented reality is one of the important applications of SLAM. We insert the ISMAR 2024 text logo and some AR objects into the replica scenes for rendering, which has better AR visualization results. We rendering the image and AR objects with our estimated camera pose. As shown in the figure, we can accurately represent the occlusion relationship between real and virtual contents via our accurate camera pose and rendered dense depth map. Thanks for watching.